Good morning. My name is Satabdi, and I'm here to talk about a series of unfortunate bugs. Why? Because I love debugging. And also, according to a study, developers spend half their programming time debugging. Now, debugging is often stressful. It induces a lot of anxiety and self-doubt. So I want to get better at what I'm spending half of my programming time. So I'm very interested in understanding how do we get better at debugging unfortunate bugs. But wait a minute, what are unfortunate bugs? So here is my formal definition. So unfortunate bugs are those which are difficult to debug, but they often have simple fixes. And they are critical, they're stressful, and they often are avoidable too. So in this talk, they are essentially simple bugs with complex behaviors. And in this talk, I'm going to talk about 4 bugs. I'm going to talk about what are they, how they were debugged, what tools were used to debug them, or what tools could have helped to avoid them, and what these bugs taught me. So bug number 1, it was a crash in a very old piece of code. So it was an assertion failure in a piece of code that nobody knew about, in a software that ran for hours, and nothing obviously seemed wrong. Does that sound familiar to anybody? Yeah? So it was a database. It was storing key value pairs onto the disk. So the client code used this database system to store the data onto the disk and then read it back. It was fast, it was compact, and it was full of low-level magic to extract the last drop of performance. Also, it was believed to be working fine, and it did work fine for more than 10 years. There was no bug found in this piece of code until one day it didn't. And it was nobody's code because the person who wrote this code and maintained this code left the company around 6-7 years back. So I started debugging this code, and I tried not to understand the code as much as possible, but it became apparent that I have to understand the code to debug further, to even make sense what's happening. So I started chasing the bug, and I started also understanding the system, and it seemed like the database system, when the client writes a data to the database system, it would first encode the data into a compact format, and then it would write chunks of the data onto some temporary database files. And before it wrote to the final database file, it would read all those temporary files back up, decode them, merge them together, and then finally encode them and write them to the database file. And the bug was in decoding code. The crash actually happened inside this decoding phase. So I started narrowing down the bug. It was tedious, and I found out the source of the bug was actually in the encoding phase. And let me give you a hypothesis. So my hypothesis is this. This distance, I call this bug distance, where the bug showed up and where the source of the bug was, and the debugging time. So the debugging time is actually proportional to this bug distance. You may talk to me later and then we can argue over it, but this is my hypothesis. So, and this is what made the bug really difficult. Now, let me show you a code, a function, and actually the function where the bug was found, it looked like quite similar. I removed a few lines which are not necessary. So does anybody want to take a guess what's wrong in the underlined code? Any guesses? Yep, go ahead, sir. exactly that was the bug. So if the shift of the right, I'll repeat what he has just said. If the size of the right-hand operand is less than 0 or greater than or equal to the size of the left-hand, promoted left-hand operand, it's an undefined behavior. So, okay, this is not working. Oh, okay. So if I pass 127 as the value, and if I pass 0, any guesses what would be the output of the first function call? Okay, so it's actually compiler dependent. It's actually an open-ended question. It's hardware dependent. It's compiler dependent. I did this in GCC x86-64, and GCC chose to not change the value. So if you see, it's a very simple bug and also a very simple fix. It's a one-liner fix. What I did in this case was I promoted the left-hand operand to unsigned long, long. I made it 64-bit, and that solved the bug. So what did I learn from this bug? So the first key learning was positive mindset. The growth mindset is very important. I could fix the bug because I kept at it. It was a long and difficult debugging process, but I still feel I could solve the bug, and anybody could have solved the bug just because if they just kept at it. It's also important to throw away assumptions. Now, what kind of assumptions? Now, this happened in a piece of code which worked for 10 years. So when I got this bug, I thought, and also a lot of people thought, that there could be nothing wrong in that piece of code, so must be something wrong in the client code. And that set me actually away from finding the bug. It was quite waste of time to find a non-existent bug in the client code. Make the test case smaller. Now, it doesn't always apply to all the cases, but in my case, it applied. So what I mean by this is try to create the failure as early as possible. In our case, in this case, the software would run more than 2.5 hours, and then the crash would happen. So how can I get the crash much faster so that I do not have to wait half an hour to get the crash? Now, I understand there is checkpoint. You can use checkpoint in GDB, but I often find that I'm not very good at using GDB checkpoint. Also, what I already covered is understand the system. It's very important to understand the system to fix a bug. And set yourself up for success. Use the right tools. We as developers often start using tools when things are already on fire. For example, I have worked on complex build systems where it's really difficult to even use address sanitizers or undefined behavior sanitizer. It's not a one-liner change. And when things are already burning, you don't want to spend time in setting up sanitizers which you're not sure whether they will even point you out to the right direction. So use them, set them up when things are going fine. In this case, if I used undefined behavior sanitizer, it would have given me the cause of the bug, and I wouldn't have to spend such a long debugging time to find the bug. Also, it's helpful to have helpful logs. Now, how many of you have written logs and then later looked at them and then like, I don't even understand what does that mean? Has anybody? Yeah, we are not good at writing logs. And I have certainly written logs where I later looked them and I felt like, is this even English? I don't know how the users even make sense of this log. So I feel it's an iterative process, and bugs help us improving our logs. Now, crash number 2, bug number 2, it was a crash right before the release. And it was a crash only in a 32-bit release executable. All the other executables were working fine, 64-bit release, 34-bit release, and debug, everything is working fine. Now, it was a Friday, and I was the last person to make change in the code. So guess who got the call when things went on fire? Me. So initially it smelled like memory error, and anytime you see something like this, you feel like, this must be some memory error, so let me just run valgrind. But valgrind didn't report anything. Also, the release build executable, as if you already know, they are built with O3, and also no debug symbols. So if you have ever debugged an optimized executable, you will find that it is actually quite difficult. So I started chasing the bug. It was a lot of manual process. You sort of, since GDB is not showing you where exactly the bug is, you start writing print statements. Okay, till this point it's working fine, and then I found out the bug was in the line where there's this explosion. So let me explain what this function does. So the function has a local variable, it's a pointer, plist. You pass plist to initialize the plist, it gets a valid address, and then you assign plist to a struct. And then you pass the struct to a function, call a function, based on some condition, and if that condition is not met, you pass the struct to another function. And after all this point, when we are trying to get the size of plist, there's this crash. So there's no obvious, I found out, and there's no obvious write to the plist. Now, let me tell you, it took me some time. I think the most difficult part was to find where this crash was happening. And once I found out where this crash was happening, I put a watch point in GDB, and then I found the culprit. So let me show you some code snippet again. So both the functions, call a function and call another function, they had lines like this. They had a buffer, which was 4 into size of unsigned long, and it was writing to that buffer. Any guesses what's wrong in this code? Yes. So in case of 32-bit, the size of buffer is 16 bytes. In case of 64, it's 32 bytes. And in case of 32-bit, it was a buffer overflow. Because already the size of the string, if you count, it's already 14. And you put another 4 bytes to it, so it overflows the buffer. But how can that buffer overflow affect plist? So that was another piece of puzzle. And the answer is, the compiler inlined both the functions. So when the compiler inlined both the function, it essentially looked like this, where both the buffer and the plist was on the same stack. And buffer overflow on debuff was corrupting plist. So what would help? Write tools, cipher coding, that definitely will help. For example, if you use address sanitizer in this case, it will tell you it's a static buffer overflow. If you don't use sprintf, it's always better not to use sprintf. If you have to use sprintf, use snprintf. You can use streams to do what you wanted to do. Also, few other things that I learned from this experience is shotgun debugging is actually not helpful. So what is shotgun debugging? Shotgun debugging is you are trying to fix some random area in the hope that it would fix the bug. So remember the plist variable which was getting corrupted. So it was late Friday night and early Saturday morning. My brain was not working, so I was like, okay, let me think what would solve the bug. Okay, let me not use plist. Let me not call the size function on plist, since I'm already assigning plist to a struct. Let me call size function on that member of the struct. Now it stopped the crash, but it didn't solve the bug. So shotgun debugging is actually not helpful. And also backseat driving is not helpful. Now what is backseat driving? So suppose I'm fixing a bug and that person from that corner shouts, hey, you should do that. That may fix your bug. So backseat driving is somebody giving you advice to fix your bug without fully engaging with you. And it's distracting. It doesn't help in any way. it actually increases the debugging time. So I got the no backseat driving rule from Brecker Center, where I spent 12 weeks. It's an educational retreat for programmers who want to get dramatically better as programmers, and it's one of the social rules there. The bug number 3 is a deadlock in code. Now, it's not a bug that I fixed. So I met Ben Dow at Boston CPP meetup, and it's a bug that he fixed, and it's a very interesting bug. So it was a multi-threaded program, and it would sometimes hang in the start, during the startup. They could generate the stack traces when the hang would happen, and it would hang at different places. They also found out no inconsistencies in locking. Also, they were using Boost recursive mutex, so no chance of double locking, they assumed, and it didn't make sense. And when they looked at the stack trace, they saw the low-level locks. You see the highlighted part of the code. So those were different. Now, if you ever see a stack trace of a deadlock, you'll see the user space logs, the logs that you are using. Those usually boil down to the same low-level log. So this served as a clue. Also, another clue was there was heavy use of singleton pattern. Now, let me show you. This is the same code. My question is, does this code look thread safe to you? Yes. Yes. So it is thread safe because the standard says so, but older C++, it doesn't even acknowledge the existence of threads. So you don't know. It depends on the compiler, actually, to make it thread safe or not. And GCC 4.2, in fact, GCC prior to version 4.3, they decided to implement this using a global shared mutex. So they would use a global shared mutex for all the static variables in your code. Now, let me explain how the deadlock happened. So imagine this. Thread 1 acquires the user space log, then thread 2 initializes a local static variable, and then that means it acquires the global shared log. Then thread 2 tries to initialize another local static variable, so it is now waiting for the thread 2 to give it the global shared log. And then from inside the static local variable initialization code, thread 2 is trying to acquire a user space log. You see? So there is this. Thread 1 is waiting on thread 2 is waiting on thread 1. This is the code, which actually I could create the deadlock in this code using GCC 4.1.2 on 32-bit Linux machine. Now, if you think about this bug is very difficult to reason, and no code review or no tools can help you debug this bug, because when we debug, we do not always start from the assumption that there is something wrong in the compiler, there is something wrong in the standard. You always start with the assumption there is something wrong in your code, and particularly you always start with that assumption when it's a multi-threaded code, because your confidence in a multi-threaded code, it's not as high as a serial code. So that makes this bug very important, and that's why it's very important to talk about your bugs. Write a post-mortem report, write a brag document, share it with your coworkers, talk at CppCon. And if you don't do it, you may forget the bugs, the interesting bugs that you'll fix. I mean, how many of you remember all the bugs that you fixed throughout your career? How many of you remember even the interesting ones? I don't, and the only way I could remember this because I wrote something about them. Art Markman is a cognitive scientist, and he's the author of Smart Thinking, and he says that to find a creative solution to a problem, one needs to find in the memory the ways to solve that problem. And I think debugging is a process of finding creative solutions to the problem. The memory of a past bug will help you in solving your future bugs. The fourth bug and the last bug is a refactoring bug. It's a classic case of cargo cult software engineering. It's a term coined by Steve McConnell, who is the author of Code Complete. So what is cargo cult software engineering? It is the process of slavishly following a certain kind of software development process without understanding the reasoning behind it. So let me tell you a story. It's almost the end of my talk. So once upon a time, in a file far, far old, there lived a function too long. So a developer came and he decided to refactor the code. So he distributed the function in two code. He cut the function in half and made two functions out of it. And instead of one function call, he would make two function calls. Now, it resulted in a crash and inoptimized executable. And the crash was intermittent. It would sometime happen, it would not sometime happen. So what is the reason of the crash? Does anybody want to guess?
It's wrong uses of setjump.
Yes, yes. So if you're using setjump and longjump, and I know longjump is old and is typically seen in C code, but we all, or most of us, still work on a large code bases with a fair amount of legacy code. And I still see setjump and longjump, at least one instance of setjump and longjump in the code base that I currently working on. And it's a purely C++ code base, by the way. So the reason of the bug is the longjump has to be in the same function or in the same call chain of the function where setjump was used. So it resulted in an undefined behavior. So what all these bugs taught me. Now this is fairly subjective and this is my opinion and you're free to think otherwise and we should definitely discuss. But I think perseverance and methodical approach is key to debug difficult bugs. You have to invest time and effort in understanding the system, understanding the bug to be able to solve them. And speaking of methodical approach, the debugging principles mentioned by David Eggins in his book is quite helpful. I did already cover some of the points in these slides, and it's always helpful to have a checklist of what are the things that you should be doing when you're fixing a difficult bug. I'm a big fan of deliberate practice. It's a term coined by K. Anders Ericsson. He's a psychologist and also the author of Peak. And I think deliberate practice helps in debugging instead of mindless practice. So when you're debugging a difficult bug, you should think what you're doing. And one of the key thing in deliberate practice is getting feedback. Now, I understand it's difficult to get somebody who can give feedback on your debugging process, but I think it's helpful to do pair debugging. So pair debugging is something like pair programming. Instead, you are debugging and somebody can give you feedback and you can also learn from that person how they debug, how do they think. The same thing has been shared by Atul Gawande, who is a surgeon and a public health professor. He also says, if you want to get better at something, get a coach. Now, there are two ways to get better. One is the traditional view, you study, you graduate, and as a professional, you take the matter into your own hand. And the other view is get a coach. Even the greatest have a coach. So that's, I think, very important. Another thing I want to tackle is there is a belief that C++ is for smart people, and I really don't like this because I think it creates an entry barrier for new people. And there is a book called The Elements of Programming Style. It's a classic book, and there the authors mentioned that debugging is twice as difficult as programming. And debugging is really twice as difficult as programming. You see the challenge for a new person who is debugging a code that he hasn't written or she hasn't written it. It's very difficult for them. I would like to say C++ is for hardworking people. You work hard, you learn the tools, you learn the techniques of how to debug, and you get better. Bugs are great learning opportunities. in any case, you have to solve bugs if you're assigned one. You might as well learn while you're solving. Don't let them go by without learning a thing or two from them. So start talking about bugs. Stop the culture of blaming. Oftentimes bugs are associated with blaming the person who wrote the code. I think that's not helpful. And believe that you can fix the bug. Okay. I took a lot of materials, and these are two of my favorite materials also. So Love Your Bugs is a talk by Alison Kaptur. She gave this talk at PyCon 2018. This video is available on YouTube. Do watch it. It's really nice. And the debugging mindset it's an article written by Devon H. Odell on communications of ACM, where he wrote how to get better at debugging. Great articles. Do watch them. Do read them. So next time you see an unfortunate bug, I hope you enjoy them. I hope you talk about them. I hope you learn from them. I want to thank a few people who helped me with the slides and gave me feedback. Ben Dow, Devamitra Chakraborty, Hira Craig, Kelson Gent, Ken Krause, Stephen Richardson. They helped me make my slides good. And I am Satabdi on Twitter. So give me a shout if you have an interesting bug. Thank you. So we have 3 minutes to take questions. If you have questions, comments, please do.
Regarding the firstmost bug with the shift of the integer, you mentioned Valgrind and you mentioned sanitizers, which makes me think that you only apply dynamic analyzers. Have you considered applying static analyzers and adding extra compiler warning levels? For example, GCC has about 20 to 40 extra warning levels that could help you?
Definitely. So in this case, I only did that. There's co-verify, which you can use. They can also sometimes definitely help you catch these bugs. I just didn't mention them, but they are like so many good tools that you should use. My point is use them. And if it requires to set them up, take the time and effort to set them up.
Hello. You mentioned backseat debugging as being bad and pair debugging as being good. The distinction in how to use those two, it isn't very clear to me. What do you consider a good pair debugging?
So in a pair debugging or in any kind of pair programming, one person is the driver and one person is doing it. So somebody is in pair debugging. The cases where I found it useful is I am debugging and somebody is watching me, and if I am making a mistake or if I am going too deep in a direction which may not help, that person is telling me, okay, don't do that, you may do this. But that person is totally engaged because he's also going through the same debugging process, he understands it. And another way which I have found useful is somebody is debugging and I am watching. In this case, I know that he's doing something and I'm like, oh, I never do that. I never think of doing it this way. So I feel that way the pair debugging helps. Like active engagement is the key. Thank you.
Okay, so for the first bug, you mentioned that it only happened after 10 years of the code working fine. So why did it only happen after 10 years and not before?
So this happened in an emulator which is used by the chip design companies to verify their designs. And the designs are gradually getting bigger. So right now, the designs are seeing designs of size which are billions of gates. So it's a matter of when the author written the code, he never thought that his code will be put to such great scale. Thank you.
Good question about the bug that only was found the night before the release. Why didn't it manifest itself earlier?
Right. So the 32-bit release executable regression, that was only fired before the release. Usually it was the practice to fire regression for 64-bit mainly because that was the main user base. I have 20 seconds if you have questions, or I'll be available outside. I think I'll be available outside to take your question and discuss. And please come find me. I'd love to know about all the interesting bugs that you have solved. Thank you. Thank you for coming to my talk.